Hi everybody, my name is Sushanta Sengupta and I thought of uploading this video. I made some slides for presentation at a different place on the RF transceivers which are being designed for cellular world today. The kind of big systems which support multiple bands, multiple modes all over the world. So I'm calling it as a world phone, and how we have come to this concept of world phone, how do we support these different worldwide bands. So just to talk through some of the details of where we started, how simple the phones used to be, and now how complex these phones have become. So I'll just share some of my thoughts in this area, and I'm just for anybody who's interested, hopefully you find this material interesting. So first let's look at some of the worldwide bands, the popular ones. Okay, so the first table here that I put in is actually by the countries. Okay, so we know that the one with the biggest penetration, the biggest population is China, there is India, and of course US is where most of the early developments have all happened here in US. But it kind of quotes all the different bands which are all over the world. These numbers which are called bands, we'll talk more in the table below what it means, but typically the number like 900 refers to frequencies which are around 900 megahertz. 2100 will refer to frequencies which are around 2100 megahertz or 2.1 gigahertz, excuse me. Okay, so this shows some of the bands which are in China, India, US, Russia, Brazil, and all that. I will let you look through these numbers, but what we are trying to do with these numbers is we'll find that there are certain bands which are very, very common. Okay, they're commonly used all over the world, and that's what, let's look at this table here, and which is what I'm calling it, and mostly it's called as a quad band. There are 4 bands, and if you look at 4 bands and you look at all the different countries in the world, you will see that most of the countries fall in this set of 4 bands. 1 or 2 of these 4 bands are there in that country, and that is used for communication. Okay, so a few years ago, and that is probably around 5 to 8 years ago, this was called quad band support. So if you could do quad band support for GSM and also UMTS. UMTS, well, I forgot the full form of this. You can look it up, but basically, standards that came up, CDMA, WCDMA, LTE, and all these are all kind of has been adopted more and more as non-GSM. GSM was the initial standard, is still a pretty dominant one all over the world, but as these others have developed, they have gone into more being called as UMTS bands. They are UMTS frequency bands. That's where a lot of those deployments have happened. So we'll talk about it more, but a few years ago it was called state of the art. So if you could support these 4 bands, and what these 4 bands will look at, it was considered very good. So let's look at the GSM quad band. Okay, what are the 4 bands of GSM? When GSM first came out, and then they rolled out, in different bands that was adopted in different parts of the world. We had 4 bands which were primarily very, very popular all over the world. One is called GSM 850. This is around 850 megahertz. What is this exact frequency? You can just Google it up and it will give you the exact frequencies for that. I think I have it in 1 or 2 slides down the road. We will see that also. So that band was called GSM 850. Okay, then the other very popular band is GSM 900. That is around 900 megahertz. Then we have GSM 1800. This is around 1800 megahertz band, and GSM 1900. This is 1900 megahertz band. Okay, frequency band. So if you took these 4 frequency bands and you wanted to go back and look at it here, you will see a lot of these countries, right, will fall. Wherever the GSM services are there, they are most probably, very high probability is that they are all going to be in either of these 4 bands. Okay, so if this does not mean that there are not other frequency bands. There are lots of other frequency bands where GSM could be supported and is also used, but at a very small fraction of it, and we will have that table later on. But what I'm trying to say is, if you have said 14, 15, 20 different frequency bands, if you took these 4 are the one where the primarily used all over the world. That's why these are the most popular bands and if you have just 4, you call it as a quad band. So if your phone could support quad band, then that's great, which means that it's the same hardware, and you can program it in software. You can reconfigure hardware in software using software, and you could program them into any of these 4 bands, and it would work, in most of the regions of the world. Okay, so that is the concept of quad band and why people were trying to build quad bands, to make sure that the same hardware can be reused at various different parts of the world. So these are the GSM bands. Then when the UMTS bands were defined, there is a lot of overlap. For example, GSM 850, that band is also called UMTS band 5. Here they don't necessarily just give it by a frequency number. They call like band 1, band 2, band 3, band 4, band 5, and so on. It's almost up to 20 some odd bands are there now. So this is called band 5, and around the 900 megahertz band, right, which is used by GSM, the same is also used by UMTS, and it's called band 8. So if you have a phone, if you're using GSM, you could be using GSM at 900 megahertz, for example, or the same phone could also support things like, say, CDMA or WCDMA or any of these other standards. Okay, then it will also use the same band, but it will be more like a UMTS band 8. We'll call band 8. You will never use both of them at the same time. No matter which part of the world you are, you could be roaming in GSM, or you could be roaming in UMTS, so you will only be using one of the two. It's not going, because at one time it can only use one of these bands. That's how these phones are designed. You will be using one of the carriers, and if you use just a single carrier, they are either going to be a GSM type carrier, or they're going to be more like a UMTS type carrier. Okay, like WCDMA, 3G, 4G, LTE, and all that. So that kind of a carrier. So coming back to UMTS bands, the 4 most popular bands is band 5, band 8, and this is band 2, which overlaps with GSM 1900. This is called band 2, and band 1 is here. This one is actually, I should have put the number, but if you look here, right, this number 2100, that is around 2.1 gigahertz is the receive frequency where you're receiving. This is band 1, and band 1 is actually the most popular worldwide band. Okay, all kinds of 3G, 4G services which are there, they were all first rolled out, and most of them in most of the countries is in band 1. This is the most popular band. And what is the frequency for this band? This is 2100. So you can say China has it. China's 3G, 4G services are rolled up mostly in this frequency. India also has it. US has it, 2.1 gig. Pretty much all the countries have a band 1, which is the most popular band for 3G, 4G type services which exist today. So these 4 bands, band 1, 2, 5, and 8, these are the 4 bands of UMTS. So imagine if you had a phone where you could support these 4 bands of GSM and these 4 bands of UMTS. Overall 5 bands here, combining GSM and UMTS. That phone will be called as a true quad band phone. It is able to support all 4 bands in both GSM and UMTS. This was considered a state of the art at that time. So after we have seen these bands, I've tried to note down only the countries which bands are used. For example, in US uses band 5 for UMTS, or GSM it would be 850. They have different kinds of carriers. Most of the carriers in US are non-GSM, like Verizon Wireless is non-GSM. But if you look at AT&T, that is more of a GSM type carrier. It has both 850 and 1900. Then there is T-Mobile, which is also a GSM type carrier that actually uses a different band, which is not shown here. It's actually shown in this table. It's 1700 is the band they use. So Sprint and all are non-GSM. So there are different kinds of carriers. Primarily, most of them are non-GSM, type UMTS type carriers. But still, AT&T is a big GSM one, so GSM is also there in US. But if you go to other parts of the world like China and India, I think GSM is still like the primarily more dominated type. Most of the carriers and their networks are more like GSM based networks. And what frequencies they use? For example, China uses GSM 900, and for 2100 is for their UMTS, 3G, 4G, all the services they have there. India, of course, has the band 1 there for those services. but India also has two GSM bands, which is GSM 900 and GSM 1800, and different carriers are in these different bands. Okay, whenever there is an auction of spectrum and the spectrum, they bid for it and they win the spectrum, and they get a certain band, and then they deploy their, that particular carrier will deploy their services in that particular band. So these are some of the bands, worldwide bands, and how we can club them into four of the most important bands, and it becomes like like what we call quad band support. So why I'm trying to show all these bands is, say we want to develop a phone which will work in both US, and if you come to India, China, it will work there. It will also work in Europe. It will work in different countries. Well, to work there, you have to have the hardware to be able to support it. So if you had hardware supporting this kind of configuration, there is a greater probability that that phone could work at different places of the world. So you can roam around, and that's how the concept came. Is initially these phones only used to support one or two bands. Then came these multiple band supports, and then using the same phone you could go to different countries, have different carriers, and you can still roam. You will still be able to use make your voice calls. You'll be able to use data and everything. Okay, so hopefully that gives you some idea about it. Now let's look at the phone subsystem. This is like a very high level picture. I wanted to describe this before moving on to how we are going to build this. Okay, but let's just look at one frequency band. Okay, we are not going to look at all these different frequency bands. It could be one frequency band. What kind of hardware is there, and how does the phone system really work for a particular frequency? So I'll start from the left side, which is the antenna. So we have the antenna here, and after, of course, there are many switches and all that could be there, but I'm just simplifying it. I'm not showing any switching network for now. What happens is the first thing that goes through is a duplexer. Duplexer is kind of a filter. Okay, so this could be a duplexer, or it could be a SAW filter. I will explain in detail what are the two different things which are there. Duplexer is for standards where you have simultaneous, that transmit and receive happen at the same time. For example, we talked about UMTS type standards. You have standards like CDMA. Transmit and receive happen at the same time. Okay, you have WCDMA, LTE, and also most of them are what we call FDD type standards. That is the frequency division duplexing. What it means is you can transmit and receive at the same time. They are not happening on the same frequency. Receive will have a different frequency, transmit will have a different frequency, but when you're doing it in two different frequencies, they are on at the same time. Okay, so those are more like FDD, frequency duplexing type standards, which is what most of the non-GSM type standards are like that. Now when we talk about GSM, then what happens is the way the GSM standard was written is, it says that you have these different time slots. Okay, at certain time slots you will transmit, then at certain time slots you will receive, and certain time slots you will do certain things which are related to the system, the whole GSM system itself, some kind of calibration, some kind of that they do in the software level. So these activities of transmitting, receiving, and all these other activities, they are broken in terms of time slots. So this is actually more of a TDD system, time division duplex. That means you are not transmitting and receiving at the same time. When you're transmitting, you're not receiving. When you're receiving, you're not transmitting. Okay, so that's the GSM type system. The GSM type systems are mainly TDD, time. They're duplexed over time, where you don't transmit and receive at the same time. All the other systems, pretty much all the other systems, are FDD, where you have two different frequencies, transmit and receive, and we will transmit and receive at the same time. LTE is mostly like that, but lately there is also something called TDD LTE that has come up, and it's kind of mostly driven by China, I guess, where you don't transmit and receive at the same time, but you're doing LTE similar to how you do GSM. Many people say it's not very effective, but some people say no, it's good. So, but those are some of the things where even LTE could be more like TDD type, time division duplexed. But anyway, let's come back to that, and let me then explain why this duplexer is for. Okay, so we are talking about mostly FDD type things. We're talking about systems like CDMA, WCDMA, LTE, HSPA, all that things which are there, right? So as you can see, there are two filtering. Looks like two filters. So what the duplexer has is, it has got one filter which is for the transmit, and it has got another filter which is for the receive. Okay, Why? Because the transmit chain will also come there, okay, to the duplexer, and it will also go to the antenna through the duplexer. Whatever we receive from the antenna is also going to go through the duplexer and come to the LNA. Since these are two different frequencies, right? You might say, hey, they are two different. Why do we need a filter? Well, the reason we need a filter is, imagine the transmit. The transmit could be pumping out power. You know, this PA could be pumping out power at say 26 dBm. Okay, that's like the peak power levels for like this, UMTS standards, almost 24, 26 dBm. So if this is plus 26 dBm, you could also be receiving at a different frequency. You're not receiving at the same frequency as TX. So imagine the first one is TX and the second one is RX. The TX is going out at plus 26 dBm. And let's say the receive is minus 110 dBm, you know, the lowest of the lowest signal you're receiving here. So what is the difference between the two? Strong to weak signal. Okay, that is 110 plus 26, which is 136 dB. 136 dB, or let's say 140 dB as an example. 140 dB is 10 million times. Okay, so the receive signal is roughly 10 million times smaller than the transmit signal. So if you have a strong transmit signal and the receive is close to it, what will happen? It will wash it out. This hardware will probably not be able to distinguish between a signal which is 10 million times stronger than this little, teeny tiny weak received signal. That is the reason why we need these filters. So this frequency separation is not a lot. You can see that if you look up, and I think I have a table later on again. I think I have a table. Well, I'll look at it later. They're not very far away. So for example, if this was band 1, okay, and these things are happening around 2.1 gigahertz, then the separation between the TX and RX, okay, that is only 180 megahertz is the band 1 spacing. Band 1 actually has the best spacing, okay, the more spacing between TX and RX. But if you go to band 2, that 180 megahertz separation only becomes like 80 megahertz. And if you go to lower bands like 850, 900 megahertz type bands, there the separation is only like 40, 45, or maybe even 30 megahertz based on the 700 megahertz bands, which are the LTE bands in US. So the bottom line is, the spacing may not be enough for this hardware to be actually able to distinguish the two. So that's why what happens is, when the TX transmits, right, we put a filter around it so the TX does not wash out the RX, and also the TX does not put a lot of garbage outside, okay, into other bands. So that's why we have a filter through which it goes out to the antenna, and that is the need for the TX filter. So we are only transmitting in the band, and the rest of it we are trying to filter it out to save our own RX, as well as to stop pumping garbage noise into the other guys who are in the adjacent bands. You could be there. Same thing for the RX. So what happens for the RX is, when we receive this signal, right? So let's say this, in this example I'm talking about, first is the TX band and this is the RX band. So when we receive the signal, the RX signal could be very, very weak, as we said, minus 110 dBm. But what about other? There is going to be a lot of interferers which are going to be there. Okay, a lot of other channels, adjacent channels, not in this band but maybe outside. And there is a mask for it, like how strong these signals could be, and those signals also could be significantly strong, and that would actually wash out the RX. So to protect that, we have this filter, so that we can actually filter out the out of band jammers, which is what we call as. So if this is our band, this is our the band that we are receiving on, then out of band jammers need to be filtered out. So that's why we have these two filters implemented in duplexer. That's what the duplexer is going to have. It has sort of a filter for the TX, it has sort of for the RX, and that provides the very necessary isolation, which is our TX to RX isolation. So my own TX, so when I'm transmitting, I don't want to be drowning my signal that I'm trying to receive. That is solved by that is being actually done by the duplexer. Duplexer is only needed, as I said, when we have transmit receive happening at the same time, which is what most of the standards are. WCDMA, LTE, and all those are transmit receive at the same time, except TDD LTE, as I mentioned earlier. Now, where do we need a SAW filter? Okay, so we'll look about that in the GSM case. We need a SAW filter. Why? The reason why we need a SAW filter is, again, in GSM we are not transmitting and receiving at the same time, so that is great news. But even when we are receiving, then what happens is, you know, you have a mask that is defined, which could be very brutal. And I think I pulled it out from, okay, where is that now? Okay, yeah. So I pulled this out from one of the slides that I had long time back from a startup. It was Serif, you know. But so this is a profile which is a standard. So in GSM, when this is called GSM blocker profile. So the signal is shown as minus 99 dBm, but actually, you know, this is for a high noise figure. Normally, the kind of noise figures this chain have, you could receive, this number is like 110 dBm. Okay, minus 110 dBm, you can receive the signal. But as you move away from it, if you just go to 600 kilohertz away from the channel that you are actually receiving, okay, then that signal could be very strong. Now remember that when we say GSM 850, GSM 900, a certain channel, that doesn't mean that it's a band. Okay, that is a GSM 850 is a band. The band is going to have many channels, like small channels like this. So this whole thing, let's see, what is this up to? 1.63 megahertz. Okay, so maybe up to here or somewhere, you can say these all could constitute many channels within a single band. So when we say a band, okay, the band has many frequency channels in it, and not all frequency channels are available to a single carrier. A single carrier, they have to be really rich to own all the channels inside a particular band. Okay, the air is the most expensive thing. Who knew that? But now we realize, yeah, this is the most expensive form of real estate, to own a spectrum. But the bottom line is, this is a particular channel which could be of one carrier. Then, you know, 2 or 3 channels down the line, it could be, you know, another carrier who could have that. So once you have it, they both could be doing GSM type transmission, they could be doing something else. So we write a standard which basically shows that the blocker profile, if from whatever your designed channel is, if you move 600 kilohertz away, it could be as strong as minus 43 dBm. If you moved 1.6 megahertz away, it could be minus 33 dBm, and so on. And finally, far out, okay, it could be even up to 0 dBm. So if you have a very brutal, you know, so this is 0 dBm and this is minus 110 dBm. Again, the received signal to the possible jammer strength is huge, right? It's almost 110 dB, almost a million times stronger. You know, again, if we take this thing, where is this one? Okay, here. So if I took that kind of a blocker profile here, and I didn't have this SAW filter, okay, so we're talking about GSM, so GSM doesn't need duplexer, GSM needs the SAW filter. If I didn't have the SAW filter, and I gave such a brutal, you know, blocker profile signal with blockers to this guy here, it'll probably wash this out. He won't be able to handle it, right? That's why in case of GSM cases, we have a SAW filter. And also the difference is, from the antenna, the SAW filter filters the receive path. The transmit path doesn't go into the SAW filter for GSM. This is only true for cases where we need the duplexer. The TX will also go through the duplexer. But in GSM type cases, GSM which is also 2G, which is also Edge is a standard, but I'm just calling that whole 2G thing as GSM. Okay, there it will go straight through the antenna, maybe through some switches. So the transmit, whenever we transmit, we are not receiving, so we are not worried about this path at all. So transmit will go straight, or based on how complicated the reference design is, will go through some switches to the antenna. Okay, so it transmits directly to the antenna. Receiving it, it will come and go through the SAW filter and then hit the receiver chain here. Okay, so these are the components here first. But let's look at what does the RFIC have, the transceiver has typically. So typically they are all 0 IF transceivers now. It's been many years, it's been over 10 years, way over 10 years actually now, that all the problems of 0 IF have been sort of overcome. They have either been minimized or they have been calibrated out after, you know, the chip is made. You do all kinds of factory calibration to take care of it. So people used to talk about a lot of problems with 0 IF, like there is a lot of DC offset. Well, we still have DC offset, but we calibrate it out. There is an automatic calibration that happens in these phones. noise is very high, the 1 over f noise for most devices only is very high, and how do we overcome that problem? Well, those kinds of have been also overcome by, you know, just doing the designs where your noise is lower, and also not to focus. See, the flicker noise is very high around DC. So if you see most of the standards now, they don't have power, you know, like they are multi-carrier systems. So when they are multi-carrier, the power is actually distributed among multiple carriers all over the frequencies. So it's not just a single carrier, a single sine wave, you know, at DC or close to DC carrying the information. That is still true for GSM type things, but still, if your thing is distributed, you know, your information and your power is distributed among many carriers, you can pretty much neglect what is at DC. So if you have very high flicker noise at DC, so what? Just don't put information at DC. Put it at neighboring frequencies, because you have a wide, you have a certain channel bandwidth. Like for example, let's say your bandwidth was 1 megahertz, okay, and you said I'm going to put, you know, every 10 kilohertz away I'm going to put a carrier, a subcarrier, and I'm going to fill up the 1 megahertz, you know, with subcarriers which are say 10 kilohertz away. And just an example I'm trying to give you. So you could actually have 100 subcarriers, right? So in that 1 megahertz range, you could have 100 subcarriers. So that way you have information distributed on all of those carriers, so you don't have to worry about that all the information is at DC and all the flicker noise or DC offset is really drowning me. Okay, so those kind of things. And of course LO leakage, RF to LO leakage causing DC offset, they're all there, you know, and especially as we have gone to finer and finer geometries, it has already gotten worse, but we have found ways to, you know, do better layout, better cancellations, and better calibration. Calibration is the key now to all these phones, because we do all sorts of calibrations to make the systems work. These have become so complex that you know, calibrations are a must. So these are 0IF systems, and this is a simple chain, a block diagram of it, which is we have an LNA. It could be a single-ended LNA or it could be differential, you know, based on, you know, whether you can afford 2 pins or 1 pin as an input. Then typically this output, these are mostly LC tuned, these are narrowband type LNAs, and we will talk about it later on in the slides. Then it splits into 2 paths. I'm showing 2 paths here. This is I and Q paths. Okay, so there's an I mixer and a Q mixer. I'm not showing the LO that comes in, they have to be quadrature LO. Okay, so it goes through I and Q paths. We have some sort of filtering that goes on. I'm calling it as a baseband filter. This could be single order or second or third, or depending on, you know, how you design it, what you need and all that, how much jammers you have to filter and all. This will also have some gain tuning in it, which is called PGA or VGA. I'm not showing that, but some kind of programmability gain is also there. Okay, gain programmability is there. Gain programmability is also in the LNA, because we have to handle a wide dynamic range. So you have to have gain programmability at various, you know, levels, the various stages here. So after you have done the filtering, you go to an ADC, and ADC is basically doing your analog to digital conversion. After ADC, the digital bits go to the baseband processor. This could be the baseband processor supporting, say, GSM standards, WCDMA, LTE, all those standards here. And then after the baseband processor, it goes to the apps processor. So this is the biggest processor which is taking care of all the things on the phone. All the software tabs, all your gaming, all your multimedia and all, and the baseband processor only does your things related to the phone, which is your voice call and your data reception, okay, data transmit and receive things. So that's a baseband processor. So I hope you already know, but I just wanted to make sure that there are 2 processors. One is baseband processor and one is an apps processor, and this is like the big processor taking care of everything on the chip. So this was the receive chain. Transmit is kind of just the reversed. You go, the baseband processor will issue those digital bit streams, right, that it wants to transmit to a DAC. DAC will convert it into analog signals, which will then go through a similar reverse chain, which is you want to do the filtering to filter out any kind of aliasing and noise effects from the DAC. Then you have the mixer, where you will actually up convert the signal. Again, we have I and Q channels. This will have quadrature LO. When you up convert it, then you add the 2. So here you have I plus JQ. So let's say if you have I channel, a Q channel, here you have I and the plus JQ information that you wanted to, you know, put in the same band, right? That is there where you're trying to transmit. Then we go through a stage which is called primarily, sometimes called DA, driver amplifier. sometimes called pre-PA, because it's a stage before the PA doing some amplification, and after that it goes off chip, because the PAs have not been integrated into all this, and the PAs are mostly the discrete components. So here you could give up to anywhere from 0 to 10 dBm type peak power you can give, okay, and then the PA will pick it up and amplify it and give it out. This could be for GSM type cases, it could be a 2G PA, where it is to pump out like 33 dBm plus 33 dBm, huge amount of power. Or if it is if it is a 3G 4G type standard that you're trying to support, then this only has to give out about 26 dBm plus 26 dBm output power, but it has to be extremely linear to meet all the linearity requirements like the ACPR and ACLR specs, and then that will actually go through the duplexer. So if it's 3G 4G PA, it has to go through the duplexer and then to the antenna, so that does not directly from the antenna come and get washed out with this the received part there. So that is a phone subsystem as a single picture, and again this is only showing one band. That's the thing that I want to stress is previously we talked about multiple bands, how do we support it, and that is what we will look at, is that if a single band, supporting single band needs kind of a configuration like this and a hardware like this, what would it mean to support multiple bands? Okay, so we will look at that. Before changing this slide, I just wanted to make a quick comment that many companies will make this as the boundary for their RFIC transceiver. Okay, it will have these blocks and this will be the boundary. So this will be one chip, and all this digital portion like the baseband processor, ADC, DAC and all, so this is the digital and mixed signal. ADC and DAC are mixed signal, they go in a different chip. So many of them do it as a digital centric chip and an RF analog centric chip. Many companies also make an SoC system on a chip, where we'll actually do all these things on a single chip, okay, and which is called as an SoC. So I put two boundaries here just to show the boundary that it could be a two chip solution like this, or it could be a single chip solution. Different companies do it in different ways, and I just wanted to highlight it before moving to the next slide. So let's go and talk about how do we do this other the multi-bands. How are we going to support multiple bands? So we have looked at this phone system, all the various blocks of the RF chain, the receiver and the transmitter part, the external filter, and this only shows one band as I talked about. See, what we are talking about here is how can we support multiple frequency bands all over the world. And along those lines we have looked at the first case, which is of the quad band support. How can we support quad band? There is 4 bands that we had in the GSM as well as UMTS. So let's look into that again, that how we can use that phone subsystem and how we can slowly build up the steps towards actually doing this support and how these things. So this is not what is the latest and greatest in what exists in the transceivers today, but this was something which was pretty hot, pretty popular, let's say around 5 years ago, okay, when people were trying to do all kinds of quad band support and make this the same hardware being used everywhere. Okay, so again I put the table here for the quad band support. We talked about GSM. There are 4 bands which are very popular worldwide: 850 megahertz, 900 megahertz, 1800 megahertz and 1900 megahertz. These are the 4 bands for GSM. UMTS, the corresponding names, even though they are in the same frequency, and I think in the next 1 or 2 slides I'll have the frequencies more, they just have a different names. Like this GSM 850 megahertz band in UMTS standard, it's called band 5. This is band 8. This frequency is called band 3. This is band 2 and band 1. Band 1 is the most popular 3G. By UMTS, when you say GSM is more like 2G, that technology that was there, UMTS came up and it finally, as it evolved, got called more and more as 3G, 4G, LTE. All that are deployed in these UMTS bands. Okay, so the most popular of them is the band 1, which is the 2.1 gigahertz. And I put the 3 main guys, US, China and India again. This is the same table that I showed previously. One thing that as you can see, I've tried to annotate something called LB. LB is low band and HB is high band. Typically when we do these designs or in our world, we try to call low band as the frequencies which are lower, up to around 900 megahertz. Those frequencies is what we will typically try to refer as low band type frequencies. So in this presentation, I will use LB or low band as the frequencies up to 900 megahertz. Then anything above 1800, 1900 megahertz and going upwards, okay, we'll call it as high band. That is kind of a convention that we'll follow here. So now let's see how this is a picture. It's a very busy picture, so I'll have to explain each point slowly, and just hopefully just bear with me so I can explain all the stuff that how we are trying to support this configuration here in this picture here. So I've noted as the US market because I am taking this first row, which is if it is the US market and you had GSM, okay, which will be 850 and 1900. So you want to support these two using hardware, okay, these two bands, and UMTS band 1 is very popular, so we'll support this. So how are we going to do these three things in a market like US? So let's look at that example. Similar things as we talk here can also be done for China and India and all the other markets by swapping hardware. So what is the goal? The goal is first of all written here. Okay, the goal is that when we make an RF transceiver for all these three markets, since they support three different kinds of flavors, we could make different RFIC transceivers. But then the problem there is once you have different types of chips, okay, different product names in the same family of chips, you have different product names. One product for say the American market, one for the Indian market and all. It just becomes too many products, and it's not easy for a phone manufacturer like OEM, like a Samsung. Okay, so if you take a OEM like Samsung, and even the best example is Apple, and I'll tell you a little bit more about them later on, about these Apple phones. But they don't want to maintain different products. They would rather like a single transceiver that they can put in, which can be programmed using software, which you can configure it and change as little as possible in the other components, which are like the filters and all that stuff. But the bottom line is your baseband processor remains the same. Your cellular transceiver remains the same. You can program those guys. You only change these external components like the PAs and filters and all to adapt to different markets. Okay, so along those lines, this is the key point: is we are going to trying to provide multiband support with the same RFIC transceiver and configurable software. The only thing that we are limiting here to changing, swapping in and out is external BOM. BOM is bill of materials, which in this case is mostly going to be, the SAW filters and duplexers and PAs and things like that. Okay, that is the only thing that they would like to switch, but keep the transceiver the same. It's also easy for the transceiver companies to actually develop a single transceiver which provides all these worldwide programmable capabilities, so that they don't have to make like 2, 3, 4, 5 different kinds of transceivers. Just with one they can address the whole market. So how do we do that? So let's take this case first, okay, and this is just an example. This is no way related to an actual phone configuration that might exist, so this is just for excuse me, this is just to explain the concept, to get the message out. So first, to say GSM 850, okay, so what I'm saying is, as I'm showing, this is the transceiver which might have three inputs. Okay, I'm calling one as a low band input going to a low band LNA, and after the LNA I'm not showing that the mixer is there, filter is there, or ADCs and all. We are not showing that. We will look into that more later on, but first of all let's just see how we are going to just, how many inputs do we need, how many LNAs we will need. We will worry about the rest of it later. So let's say in this example you have one low band input. Okay, this is a low band LNA. This is going to be more like a narrow band matching, and we'll talk about LNAs more later, what the topologies look like commonly. And we have two high band LNA. Okay, so what I'm saying here is, let's take an example where this first one, right? So they have this PCB made, which is what we call the phone reference platform or the phone reference design of the phone, and they have a slot here to put a component. This component could be either, they could populate it with a GSM 850 SAW filter. So there will be a SAW filter for the GSM 850 MHz band. If they put it in, that means we are supporting the GSM through this path. Now if you don't populate the SAW filter and say I'm going to put a band 5 duplexer, okay, then you will be able to support this UMTS band 5. So either of the two can be supported, but not both at the same time. Okay, in the same path you can only put a single hardware in the phone, and you are not able to program these SAW filters. You cannot switch between SAW and duplexers unless you have a switch and all that. But here we have either the SAW filter, so we'll support GSM through this path, or we'll have the duplexer where we will support, you know, the UMTS frequency here. So if it is the so this path going in pairs up actually with this path here for the transmitter. So let's say we have a DA path coming out low band. It would either go through a PA. If the PA is a GSM PA, like if this is a GSM SAW filter, then this will be a GSM PA, right? It will go straight. It will not go into the SAW filter. It would try to go straight to the antenna through some switches which will be here. I have not drawn them because those switches could be in different configurations, different kinds of topologies and all that. But let us just assume that this, if it's a GSM PA, it goes to the antenna eventually. Okay, so this becomes your receive path for GSM 850 and the transmit path. Now if this path is not with a GSM, but you're saying I'm going to support band 5 UMTS, okay, could be CDMA, LTE, WCDMA, whatever you're trying to support through that path, then you will have the duplexer, and this PA at that time will be actually not a GSM PA, it will be a 3G, 4G type of linear PA. Okay, that would be that PA. So here again, when I say PA, you can swap it based on whether you have a SAW filter, you populate this part with a GSM PA, or you populate it with a linear 3G, 4G UMTS PA. Okay, so that UMTS part will not go straight to the antenna, it will go to the duplexer, and then through this duplexer it will go to the antenna. So this first path is an example where you can support either the GSM 850 or the UMTS band 5. The other one is going to be, right, for the next case, which one is it here, GSM 1900. Similarly, I'm saying that you can have you can populate a GSM 1900 SAW there, which will go to a high band LNA. So this will become to support the GSM 1900, and similarly in the DA path, this is the high band where you could have a PA which could again be a GSM PA. This would be for GSM 1900 band, and it will go straight to the antenna. Now if it is not a GSM but you are supporting UMTS band 2, you could put the duplexer here, have the PA accordingly, and that will go through the duplexer and go out. Okay, so what we have done is we are saying with a single low band input we will support either the GSM and UMTS. High band, one of the high band inputs, we will support the 1900 MHz band, and then we have band 1. Band 1, if you see, is the most popular band, and this is typically what will always be there is you will have a dedicated path, in this case shown as high band. It will have a band 1 duplexer. So this is the input. It will have a DA, a dedicated path for high band out, going through a band 1 linear PA and going through the duplexer. Okay, so this would most of the phone platforms will always have a dedicated band 1, because band 1 is the most popular 3G 4G band worldwide, and they will always have a path with a duplexer and a PA to support this band 1. The other paths are programmable in the sense that you can program the RFIC in software. Okay, but these external components, they cannot really be programmed. You know, whether you need a SAW filter or duplexer, no, these are two separate paths, two separate components. So you just have to you know, put in whatever, you know, you're trying to support. So based on that, so let's say, you know, in US markets, if you wanted to support GSM 850, GSM 1900 and UMTS band 1, then this will be a SAW filter. Okay, this will also be a SAW filter, and this will be a duplexer, okay, with its own linear PA, and this could be, you know, two of the GSM PAs. So this is again for an illustration of how you could do it, and based on this, what happens, a guy like say Samsung or Apple, right, the OEMs, they will actually make a phone reference design, it's called, where they will say, you know, for this particular region I'm going to support these bands, so they will put the corresponding filters here, what kind of filters they need, what kind of PAs they need. RFIC will not change. Okay, so they might have a reference design, phone reference design for the US market, where they say, okay, these are the filters, these are the things. Then they go to India and say, you know what, Indian market is different. I don't need GSM 850, I need GSM 900. So they will replace this with a 900 megahertz SAW, and this one with whatever GSM 1800 megahertz, and say, you know what, this part remains the same because this is common between the UMTS band, one is common between US and India. So they have this so they start from a single reference design, a phone reference design, which is basically a PCB with all the bill of materials. What is the RFIC transceiver, what is the baseband processor, what are the different duplexers and filters, switches and all that they need, and from there they derive different phone designs for each of these markets. So they start from a single design and maybe come to 4 or 5 different flavors of the PCB with slightly different kinds of components based on what band duplexers or what band saws are there, and then just simply go into volume production, and all those PCBs end up being different phones, right? So that's how this support. So here in this case, as we were talking about quad band support, by doing something like this where the RFIC transceiver is common, and just by replacing or changing out the external components, you are able to do quad band GSM support as well as quad band UMTS support, okay, in most of the countries. And this is just showing, this is a very simple example. This is not how it is. It's much more complex than that, and there are many combinations possible of what are the different flavors in the worldwide, and which bands we want to support, which bands we don't want to support, which bands are common, and things like that. But hopefully this gives you an idea of how you approach this, tackle this problem. By the way you solve it is try to minimize the number of external components that you have to change while keeping the RFIC transceiver and the baseband processor and everything the same. So some of the points are added here. So here if you see that each LNA will need 2 inputs if these are differential. They are used to be differential, but lately they have been changing to single LNA inputs because they need a lot of the pins, and the pins are becoming a problem. We'll talk about it. This does not show any receive diversity. So I'm just showing one set of inputs, but we have something called diversity, and we'll talk about it more. Those are there to to be able to receive high data rates, and that adds more complexity because it will need more LNAs and more input pins, and we'll talk about it next. Then on top of receive diversity has come LTE and then LTE-Advanced, which is LTE-A carrier aggregation. That is, even with first we had just the normal things, people started using data. Then they added diversity paths, which I'll show next, to increase the data rate. Even that wasn't enough. We were like, our appetite was way more than what the hardware could support. When receive diversity is not enough, then they introduced LTE. Now LTE carrier aggregation to support, that the appetite for data. Then things like SHDR was there. Now it's LTE-A, MIMO is coming. All kinds of stuff is happening, and it seems like the more you give us, the hardware gives us, the more our appetite goes bigger for data. So to support this tremendous data growth, all these things, and I'll try to talk briefly about this. One thing that I want you to keep in mind is as we go on, I/O pins will become very, very important, and I keep stressing on these a little bit, but I'll stress on it more and more, is you can put more and more hardware, and as your I/O pins, these input output pins become bigger, it is actually becoming a problem. Why is it becoming a problem is, when you do a design, and as I will show these things, these systems are very big, massive, complex systems with lots of blocks, right? You might think that, oh, these blocks are going to be big enough, and if you put all the blocks, that determines the total die area. So when we say how big is the die, the normal answer comes is, hey, let's take all the blocks and do the layout, and whatever we can fit, right, in some x by x dimension, that is our die area. That used to be true in the earlier chips, okay, where that is what we call as the die area limited, means the blocks in the die itself is limiting the die area. Now what is happening is all the circuits have shrunk so much that the blocks take certain amount of area to fit. But then you also have these I/O pins that have to be there. These are like whether you have a flip chip type of package technology or all these wafer scale packaging technology that you have. Those package balls are right on top of the die, and as this number of package balls are increasing, right, the number of I/Os are increasing, we find that, hey, our die is, the circuits are really shrunk down, it's good, our layout has shrunk and our whole die area is shrunk, but now you know what the problem is? We are not able to fit our I/O pins in it. Our I/O pin balls, which has to go on top of the die, the number of balls are just too high and I'm not able to fit it, so I have to grow the die because I need more I/O pins. Those things are what we call I/O limited, and most of these designs are now, the die area is getting limited by the number of I/Os we need. So in a sense, it's not limited by the area of the circuits itself, it's limited by the area of the I/O pins. So reduction in I/Os is a key thing in most of these chips to make them smaller, and they have to be smaller. You can't just make them bigger and bigger, it's expensive, it doesn't fit on the phone. So there's these I/O counts are becoming extremely important, and all kinds of techniques to reduce I/O counts are very, very important now, because most designs are I/O limited. The die area is limited by the number of I/Os we need and the area of this I/Os, which are basically the balls or bumps, whatever you call it, which are eventually going to the package. Okay, so let's look at a few other things. We only looked at the quad band, right? The 4 popular GSM bands and the 4 popular UMTS bands. What are the other bands? So there are many other popular bands that have moved on and has become very dominant and has become very popular and very important to support, and I try to note them here. So in US, 700 megahertz bands, which used to be a lot of the TV channels, higher end UHF frequency spectrum TV channels, they have been made free now because of digital TV, and those bands the government has auctioned and allocated it for the LTE services. So LTE services in US didn't come up in these bands. These bands were already choked and congested. There wasn't any much space, there room to develop LTE in it, so they gave 700 megahertz, around 700 to 750, 760 megahertz. They have many TV bands which are freed up primarily to support 4G LTE in US. So these 700 megahertz bands are very, very important bands. And I have a table here which shows, and I will go through this table. Basically what it says is these are UMTS band number. Okay, so we talked about band 1, which is the most popular band. The frequency is around 2.1 gigahertz. Then we have these two columns, which is uplink frequencies and downlink frequencies. Uplink is for transmit. So in this band, if you're operating, the transmit frequency ranges are here, 1922.4 megahertz to 1977.6, and within this is a band. It has got many channels. So there will be many carriers who have won the auction of many channels, and they will all be, their subscribers will be transmitting in this band if they're in band 1. Okay, so this is the transmit frequency that happens, and this is the receive frequency. And the duplexer, what it does is, as I showed you the picture previously, is it has a filter for this transmit and a filter for this receive that it implements for the various reasons that we talked about earlier in our lecture. Okay, and if you look at the transmit and receive, the separation is 190 megahertz. Yeah, I think I apologize, I made a mistake previously saying this separation was 180 megahertz. It's not 180, it's 190 megahertz. That's called the TX transmit to receive separation. Okay, so this is what each of these entries in the row means, and this is band 1. Similarly, you can go through band 2, 3, 4, 5, 6, 7, 8. 5 and 8 are the other bands that we talked about. So all this is there, and you can see the separation becomes really, really small. So when RX and TX are very close, it becomes very difficult to actually get good duplexers with good rejections, and sometimes some of these smaller separations become a challenge, especially for 700 megahertz. When we come there, we'll see that. So band 8, then there is band 9, 10, 11. Then here are the bands, around 700 megahertz. Band 12, 13, 14. There is also 17 and all which are there, but I think this table is, I don't know where I copy pasted this table. So there are more bands here, which you can Google up and see more frequencies. But the point I'm trying to make is, around the 700 megahertz, there are different bands, and they have been allocated to different carriers in US, and that has been primarily to develop the LTE services. So the bandwidths are really small. Okay, so for example, you take this 30 to 43 megahertz, right, which is about what, 13 megahertz. So if you have 13 megahertz bandwidth, the LTE supports many bandwidth modes up to 20 megahertz. You cannot support 20 megahertz here. It is also going to be hard to support 10 megahertz, because if you do 10 megahertz, you're giving that whole 10 megahertz to a single carrier, a single service provider. So this does not even support 10. They are more like 5, megahertz LT 5 megahertz mode or lower. So based on all this, many of the bands are also combined to support LT 20 megahertz in some cases, based on what kind of auctions those carriers won or what kind of tie-ups they have with between different cellular carriers. But these are the 700 megahertz bands which are also important. So I think I should go back to this first bullet. So these are important bands that has to support that were not there in that previous table I talked about of quad band. T-Mobile USA, they came to USA and then they have become very big, one of the big carriers in USA. They actually use the 1700 megahertz band, which is UMTS band 4, this band here. That doesn't fall in the quad band support. So this is also a very important band to support because of the presence of a big subscriber base there for T-Mobile USA. There are upcoming 2.7 gigahertz, it's not upcoming, I think it's already there now, 2.7 gigahertz bands in China. So that is kind of the highest frequency that was there, and they are actually pushing it higher. I think there are certain bands coming up which are even going to 3+ gigahertz. I don't know the exact frequency number, but those are also coming. One of the other points I made is Qualcomm CDMA when it started, it was at 450 megahertz. Most of them don't support it, but still this support is still there in some of the older chips. So this is another band which is not in the quad band that has to be supported. So you have the quad band frequencies we looked at. We looked at some example of how by swapping different filters and duplexers and PAs, you are able to do quad band support. This only gets much more complex when you have to support more and more frequency bands. Okay, so with all these things, now we are moving to the Volt phone, like supporting many more bands. But before getting there, let's look at receive diversity. We talked about it, but I just wanted to explain a little more in case you might be already familiar with it, but just bear with me so that for the sake of everybody, I can explain a little more about it. So what receive diversity was introduced many years ago to increasing the data rate. When we make a phone call, we just use the primary path, and for voice calls this is enough. But when we are trying to receive data, imagine rather than having one stream, if you had two of them working in parallel, okay, you had two parallel paths, okay, then technically you can think of, hey, I could get twice the data rate. Okay, I have two paths going, I could have some error in one, I could have some errors in the other one, bit errors, but if I combine the two, I'll have a better bit error rate and I'll have a much higher speed, of decoding, of receiving. With that concept, the receive diversity was introduced. This is doing in the same frequency. So when you're receiving the same, except that there are two antennas. The primary antenna along with switches will be there. I'm not showing switches in any of these things. So we have one stream that comes from the primary antenna that go through these three paths that we talked about earlier. Okay, and now we have an extra antenna called diversity antenna. It will be receiving the same kind of signal in the same band, and that is the second set of paths. So you have two parallel paths always on. So you could have, okay, let me explain this. PRX. PRX here means primary RX. DRX means diversity RX. Okay, so that's what it means. So previously we had this low band primary RX path with either the SAW filter or the duplexer we had. So this is same as the previous examples. I'm taking this example and just simply showing how we will add diversity. The TX path will also be there. I'm just not showing it because then the picture will become too crowded here. So the primary paths have remained the same as we had previously, one low band and two high band, and for each of this path that you will use, right, each of this only one will be on at a time. So whichever is on, you want a corresponding path here in the diversity. So I've labeled the same thing as low band diversity, high band diversity, high band diversity. One thing you notice is they don't have their filters, and the reason we need these duplexers here, right, is primarily, and again, diversity is not there in GSM. Okay, GSM does not support. Actually, now I take it back. I think there are certain things which are not GSM but GSM type old legacy modes where we are adding diversity. So we will look at it. But let's just for this for this discussion, diversity. Let's just assume that diversity in most cases is only applied to UMTS type things. That is for where you have duplexers there. Okay, so what the duplexer is trying to do is it's trying to separate the TX and RX. The TX could be transmitting in much strong power. We don't want the TX to be drowning our own RX. That is the primary use for it. So in the primary paths where you have the TX, right, the 3 TX that goes out, as we showed, the PAs go through the duplexers. So that would still be there. But what we have done is we have added some extra diversity elements. Those diversity, what happens, does not have any TX associated with it. This is only receive diversity, which is what most of the chips have, where we are trying to increase the data rate of reception. Transmit part has still remained the same. Those transmit things go and hook up to these duplexers because they have a potential to corrupt these primary paths. That's why you're using it. But in diversity, since we don't have any transmitter feeding into these lines, we also don't need these duplexers here. They could just come straight from the diversity antenna through switches. Switching will be there. Whatever switching is there for primary will have the same kind of switching for diversity that will come. And these paths mostly have a little more relaxed spec compared to the primary. So the primary paths could actually see much more stronger jammers, much more stronger transmit power compared to the diversity, since it's a separate antenna. That is, even if the primary antenna is getting the transmit power, there is enough isolation from the primary antenna to the diversity antenna where we don't have to worry about a very strong transmit coming here and drowning us, killing these things. So now you can see that just supporting reverse receive diversity, what it did, it will double up your hardware and double up your I/O pins. And this is a must in all the chips now. I'm showing, in this case only 3 inputs. So 3 inputs primary and 3 input device, so 6 inputs. The actual transceivers nowadays are way more than this. They are approaching almost a number of 30 inputs, 30 combined inputs for primary and diversity. So you can imagine how big these chips have become, how many different bands and modes they support, and how many LNAs they have. So it becomes a challenge to have so many LNAs and so many inputs, and they are really becoming one of the most complex systems. But anyway, coming back to diversity, so hopefully this explains that you have the data stream coming in, which will be decoded by a primary ADC. You have the same data stream coming in another parallel path, which is a diversity path given by the diversity ADC. So given that they both are receiving it in like 2 of them simultaneously, through all the math and all, you can show that your data rate is going to be higher. But intuitively, it's saying that even if you have loss, a little bit of loss in one channel, the other will take care of it and vice versa, and that's why the data rate is higher. So this is diversity, but diversity comes at the expense of almost doubled hardware and the number of pins, and of course it needs the other antenna also. But this is a must. This is a must in the chips. So after the diversity, let's look at carrier aggregation. This is the new thing, the most latest thing that all the companies are trying to address and try to support. So when LTE came up, LTE had modes up to 20 megahertz, and they could support very high data rates, but they also found that that is not going to be enough. We need to do more than that. So they went from LTE to LTE-Advanced, which is LTE, -A. That is, A stands for the advanced, and that includes carrier aggregation. So what this basically says is you could have 2 different kinds of carrier aggregations. One is intraband, interband. But before getting there, let me try to explain what it means. So let's say you are a carrier and you are trying to send your data through a particular channel, okay, and that provides some data rate. Now if you could send 2 channels, okay, don't worry where those 2 channels are, but if you could transmit a high-speed data through 2 channels, then that would increase your rate of reception. So you have diversity improving your rate, receive diversity, and on top of that, now you have, rather than just transmitting at 1 channel, you're saying that you will do it in 2 different channels, okay, and that is called carrier aggregation, where you don't have 1 carrier, you actually have 2 carriers. Now, are the 2 carriers going to be close enough, far enough, and all? And based on that, we have these 2 categories called intraband and interband. So intraband means, intra means it's within a band. So this is an example that I took out a picture from the 3GPP website. They have this explaining it. So we have this case called intraband contiguous. So think of three of these guys, right? So you have one channel where you have data coded here, which is blue. Next to it is green, and there is red. Let's say they are all together, contiguous, and they are all inside a particular band. Let's say this is the most popular band, band 1, and they are all inside a band. Then it becomes intraband. Okay, so they are all inside a particular band. You could also have another case of within the same band, which is intraband but non-contiguous, where these two could be your channels where the information is, and the next one could be somebody else's. Okay, and there are many channels. It's not just 4. There are many of them. This just shows an example that where your information is spread in the same band at different channels inside the band, and they are not contiguous. So you could have contiguous, you could have non-contiguous, but all within a single band, and that is the intraband. Now what is interband? Interband is also possible where you have two different bands. This is not a very good example, but they should say more like, say, band 1 and maybe band 5 or band 8 or something like that. But take it as, so this is a band 1 and band 2. These are two separate bands. Don't correlate these numbers with the bands numbers of the UMTS band. Okay, but this is one band and this is another band. What you could have is, you could have these information spread actually at two different bands. And when these bands are different, right, they are called interband. That is, the information is not in one cellular band, it could be in two bands. For example, if I go back, where was my table here? Okay, so maybe I should just go back to this table and try to explain. So I could have a case, and a lot of popular cases is band 1, everybody uses it. This is where you could deploy LTE. Now when it comes LTE-Advanced, and you are not able to get enough channels on this band, you might say, I have band 1, and I also have a different band, a lower band like this. Okay, could be say 850 or 900 megahertz. So I'm going to have the information simultaneously go in two frequencies, band 1 as well as, say, band 8 or something like that. When that happens, then you have a low frequency band and a high frequency band, and they're both primarily together. You could also have another case where you can say I have band 1 and I've got band 2 also. I'm going to transmit it in both these bands. So some part of the information is going here in band 1, some of it is going in band 2, and then you have that combination is more like a high band with a high band combination. Okay, so that's what you could have. So based on that, right, so intraband, you could actually have different combinations. You could have a high band with a high band, where the data is being received simultaneously. You could have a high band with a low band pair. It's a pair, so you could have one of them could be high band, one of them could be low band. You could have two low bands. You could have low band with another low band. Okay, so all these combinations based on the worldwide, which carriers have what spectrum and what they can use, and this has been encouraged because most of the carriers, they can't really win two bands type of spectrum. Let's say a carrier which says I have a high band frequency and I also have that's a lot of money to be able to own two bands of two chunks of the spectrum, one at say higher frequencies, one at lower frequencies. But what they said is, what, why don't we tie up and make we become friends, and we say that, hey, I own a low band, but why don't you allow me access to, you own a high band, and why don't you allow me access to high band where I can do carrier aggregation in my low band because I own it, but I will also partially use your high band spectrum whenever it's free, and I'll pay you money for it, right? And similarly, you can do the same thing, is you can do your all the transmission reception in high band, and let me own a part of the, give me some, and I'll give you access to my low band, so you can also use it, so that effectively at the end we are improving the efficiency of a spectral use. Spectrum is expensive, people need data, let's use the spectrum efficiently. Okay, so with those goals, this whole thing was developed, and along those lines, you have these intraband and interband type carrier aggregation scenarios. So hopefully I have not confused you too much, but please feel free to look up. There's a lot of literature in the subject to get more information. Now, okay, so this is the standard. They're trying to increase the amount of data rate diversity, and now through carrier aggregation. What does it mean for us? Let's say if you are the RFIC transceivers guy and trying to design it, what does it mean? So let's take a case of intra-band, okay, where you have an antenna where you're receiving it. Here is the duplexer showing TX and RX. Let's assume it's more something like band 1, UMTS band 1, where the TX is lower than RX. And you are actually transmitting in two different bands. One is yellow and I'm sorry, not yellow. It's a green and red. Okay, so these are the two things that's coming. They are two different channels. Okay, so you're transmitting it. What do you do with it? What does it mean for the hardware? So one possible way, this is only showing one possible way. Different companies have different ways of doing it. I will not go into those details, but I'm just trying to show one possible way to get you thinking, and then you can come up with your own, intuitive, innovative ways of how people can, do it and make the hardware less. So we could use the same LNA path to go through it. Then we can split into two paths. So we have the green guy and we have the red guy. The green guy goes to this signal path where the LO, the frequency that's coming from the VCOs, and after some division, okay, that is going to help decode the green guy so that after down conversion, the green guy looks like this. And then that green information gets filtered by the low pass filter and goes to the ADC. So this ADC will be processing the green information. Similarly, just by shifting the LO, which has to come from another synthesizer, so you can see that you have a green LO and a red LO. These are two different frequencies. That means it automatically tells you, rather than having one frequency synthesizer, you will need two of them to do something like this, just because they are in two different frequencies. So this red one could actually down convert such that we can filter out the red guy which is in band and everything else. So the green guy is out of band here. If I consider this, red is in band and the green is out of band. Green gets filtered out significantly. Then goes to another ADC. So what it has done is it has doubled the number of ADCs. It has doubled the number of synthesizers because you need two different frequencies, right? So that means a lot of area, a lot of power and all that stuff to support intra-band in this way. It has not increased the number of input pins, so you can still use the same input. So that's a good thing. You can still use the same LNA front end and split the output to do this, but it has doubled other hardware in the circuit, even though it has not increased the number of input pins. Now, one point I want to make specifically to this scheme is, if you have one LNA and you're splitting into two parts, you can see that you're losing 6 dB of signal, right? Half of the signal. Half of the signal is going here, half of the signal is going here. So the gain, so if you have the same LNA as before, the gain becomes less, means your noise figure will go up, right? So what you have to do is, you actually have to make this LNA as more like a 2x stronger LNA. So if you had a normal LNA, now you want to burn twice the amount of power so that you can still maintain the same gain from this input pin to this ADC input, both for the green signal as well as the red signal, so that you can effectively maintain similar kind of gain and similar kind of noise figure numbers, so that your SNR values and all that for carrier aggregation. That's the case of carrier aggregation with two channels is similar to if it was a normal case where there was only one channel, no two channels, okay, just one channel, you had good gain, good noise figure, good sensitivity and all that, you can maintain that. So sometimes this is not desirable, the splitting of the two and losing half of the signal. There are other tricks people play and I'll let you think about it, but this hopefully explains that if you have two different channels, then how you need two different kinds of synthesizers and two different filtering chains and ADCs to be able to actually process this received signal. Now you might also think that, say that, hey, if this signals, why do we need two chains? Why don't we just pass the green and red together? We put an LO somewhere in between the green and red and do that. You can do that too, where you can avoid completely the other chain. But what it does is, most of the time, based on how far they are, it would put a lot of stress. So it will require a single synthesizer, but then the filtering, it will put more stress on the filtering because the filter has to be wider. And if the filter is wider, many of the interferers could come in band, because now you widen the filter bandwidth to accommodate both the green and the red. They might come in band and it will cause saturation problems for the ADC. You could have a whole lot of other problems. Power will go up, ADC, can it support such a wide bandwidth? Just by increasing the bandwidth of the low pass filter and burning more power in this filter might be okay for the filter, and it might be able to still, deal with the interference and all that. But when we go to ADC, widening the band of the ADC and still saying, we need good resolution, that is not a simple, straightforward linear scaling that happens in ADC. So all these constraints could put a lot of pressure in terms of the reality, whether you can actually design such things and how high the power would be. So in many cases, we break it into two and we say, we're just going to have two synthesizers and just do it this way. So this is just, as I said, one possible way. But people are working and finding creative ideas every day to solve these kind of problems. Okay, so I think I already talked about these things here, but this is one possible way that if you had two channels within the same band, how you could do this. So this is called intra. Now we go to the inter. Inter is where you actually have two of these which are in different bands. So for example, if I draw them far separated in frequency, right, the green and the red, they're separate in frequency, then the green might be in a particular band whose duplexer we need, and the red might be in a completely different band which is out of this duplexer. This duplexer will completely attenuate it, so we have to have another one. So we'll have the same antenna through some switching network which might be there, but we will need two separate paths now. So for example, this I'm showing intra band between a low band and a high band. Okay, low band being the lower frequency being the green signal, and red being the high band, high frequency signal. So here we will actually need two different duplexers, two different LNAs, and then everything inside. Of course, we will also need two different synthesizers, right, because these are two separate ones. These are going to be different frequencies that we need to down convert it. Then we have the filters, the low pass filter and ADC is again 2x. So hardware wise, we have two synthesizers as we had previously. We had two chains, two ADCs and everything to support carrier aggregation. What has gotten worse here is we also need separate LNAs, because a single LNA, which are mostly narrowband type matching, as we will talk in a few slides, cannot actually receive both low band and high band signals through the same path. They have to be wideband LNAs, and once you go to wideband LNAs, power goes up, lots of other problems, filtering of the jammers and all that comes. And so this is also increasing the number of I/O pins, which is bad, because more and more I/O pins are limiting the die area, and it's also increasing the hardware a little bit more in the LNA. So overall, having carrier aggregation, increases the hardware, increases the power, increases the I/O count, and it is, even though the standard is good, where you say, hey, I have got more than one channel to transmit, from a hardware perspective, it's actually very cumbersome. Okay, and it causes a lot of challenge to support carrier aggregation. But carrier aggregation has been implemented and is coming up there, and it will only at the end help boost up higher data rates, and guess at the expense of what? Your battery is going to drain out even more faster. The power is going up. So this hopefully explains the carrier aggregation concept of both interband and intraband. And now we'll look at one example, and this is again just an example that I'll try to talk through it. I haven't put a lot of text. It's a very busy, confusing picture. But my goal is that, hey, let's take this example and see what are the different things we can make it work in an example like this. Can we support, a intraband, interband, and as we talked about previously, we have diversity, we have say quad band support for GSM, quad band support for UMTS. How all can we do that? So this example just kind of I'll walk through this verbally and see that if it makes sense to you. Again, this in no way represents anything that's done in the industry. This is just for the sake of getting the message out. So let's take this example where we have 1, 2, 3, 4, 5, 6. Okay, 6 primary inputs and 6 diversity inputs. So what I'm showing here is 12 inputs, right? 12 inputs with 12 LNAs, and not necessarily 12 signal paths, but we'll look at it that what we actually mean here. And again, even though this is only showing 12, as I said, the current day transceivers are approaching this I/O counts to support LTE Advanced, to support diversity, support all kinds of features, to almost 30. Okay, so these chips are becoming humongous huge in terms of how many paths they can have. So let me start with it and say, so how many high band paths I have? I have got 3 high band paths here and 3 low band. Okay, and why did I put it here? So first of all, let's look at this path. This path I put in because this might be a high band carrier aggregation path, high band carrier aggregation PRX, where what we are trying to do is, this is interband. That is, if we have this example that we took about, right? So if you have interband going on, not interband, I still get confused with these things. It's intraband, within a band. So it's intraband. So if you have a case of intraband CA, how can you support it? You can support it this way. You have an LNA, you split into the 2 mixers. They will have 2 different synthesizers, which I'm not showing here, the synthesizers that will supply you the LO frequencies. They will go to 2 different paths. So this path will be there for intraband carrier aggregation. This path will be there through this filter and then go through the ADC and finally going into the baseband processor here. Okay, so this will support high band carrier aggregation with intraband in high. Okay, intraband within the high band 2 channels. If you have the primary support, you also need to have the diversity support. So this shows this, the high band carrier aggregation with diversity. Okay, the same thing copied over. Now if you were to do, you said that okay, carrier aggregation I have to do, but I am not doing the intraband, I want to do interband. So if you do interband, you could have a case, just take an example, let's say high band with another high band. Then what you can do is you can use this to turn on one path, right? You can go through, say maybe, you know, this path and this filter as one of them, and you could use one of these 2 high band paths, then its mixer and then the filter to go through it. So I think the way it will work is, if you're using any one of these high bands, right, you're going through this filter path, the top filter path. That means for the top one, we have to use this path, which is LNA, this mixer. Okay, not that mixer, this mixer. Come down, then use this filter path and go out. So these 2 become then the 2 channels which are there in 2 different high bands, 2 different frequency bands, which are 2 different high bands doing carrier aggregation. So using one path you can do intraband, using 2 paths here you can do interband, and again interband doesn't need to be only high band to high band, right? It could also be high band to low band. If that is the case, then you could do, you know, any one of these the low bands. Okay, so this one is again for, if you can use any one of these low bands to do that high band to low band carrier aggregation. Why do I have this path? This path is there similar to the high band path. When you have carrier aggregation in high band and you have 2 channels in high band, which is the intraband, right? This first case, intraband. If the intraband carrier aggregation was happening in high band, you use this path. But what if it was not high band, it was low band? Then I have this path for that. So it just will have the duplexer, which is the low band duplexer. Okay, I'm not showing the duplexers here, but all these paths will have either a duplexer or a SAW filter in front of it. That is what I'm not showing, but that I hope you get the message that the duplexers or the SAW filter will there for all these paths here. Okay, the diversity will not have it because they really don't really need it. So these could be straight shots, you know, to the antenna. Sometimes they might need some filtering based on how strong the signal is coming, but most of the time they don't need that. Okay, so now what are these 2? These 2 could be, you know, you could have a case where you say, you know what, I'm going to do either one of them is a band 1 in high band. I'm just doing the normal. If you don't have carrier aggregation and you want to do a band 1, you can put a band 1 duplexer here. So this provides me band 1 UMTS support, and maybe put a SAW filter here, like GSM 1800 or 1900 SAW filter that you need, and this path I can turn it on when I have 2G support. So this could be a simple 2G support case with a SAW filter here. This could be the 3G path, say band 1, band 2, something like that, a 3G path based on what duplexer you put. and you are going to have either of the two, right? You're not going to have both of them on at the same time. That's why they go to the same mixer and then through the baseband filter and go out. So hopefully that way it's clear. And same thing here is for low band. You could have a UMTS path with a UMTS duplexer with a GSM saw here to support GSM type 2G. So one path could be 2G, one path could be 3G. Okay, and with all these extra things added, so you are able to do 2G, 3G band support. You're able to do intraband, interband in an example like this. But again, you might need to support, well, a phone configuration might say, hey, I want two low band, two paths for 2G, and I want two paths for 3G, and then on top of that I want another path for carrier aggregation. So it'll be like 5. Then you might have to support more than this. It might be 5 of them for high band, 5 of them for low band, or something like that. So deciding what are the different bands you're going to support, what are the different things you're going to support, like intraband, interband, and all this. That is the first complex task that happens in the industry. Is system guys, they sit down and try to scramble their heads and try to come up with all possible combinations and all, and how to come up with the hardware where they can actually support the most without changing the hardware. By hardware in this case I mean all these duplexers and SAW filters and switches and everything. Okay, this is only a subset, a really small, it's a mini example compared to how complex these systems really are and what you have to do to actually do this. And when you do that, you decide, okay, I need so many input pins, I need so many LNA paths, so many mixers, so many frequency synthesizers, so many filters, ADCs and all, and then you come up and you say, oh, this is going to be a very big, massive, complex system. So hopefully through this example, it kind of gives you some idea about how to just support the legacy 2G, then 3G, 4G paths, and now carrier aggregation. What is coming more next is MIMO, which is basically, you're going to have diversity, carrier aggregation, and also multiple paths. They just simply doubling the number of paths, doubling or quadrupling it, like Wi-Fi uses. So that is also going to require more and more parallel paths, LNAs, mixers and all that, and also their IO pins to kind of work there. So that's what's there. This now next let's look at all the RF blocks in more detail, that how we actually design the blocks, what this topology looks like and all that. But before going into this, since I was talking about it, there is one thing I do want to mention here is, I think in many cases, let me go back here and say, so this is receive diversity, maybe not, maybe here. So I think the message I'm trying to say is, if you do 2G support, right, 2G is an older technology, it is still necessary, so the phones have to still support it because a big part of the world is still 2G. So the 2G needs SAW filters, right, and there is a big push right now to become SAW-less. So industry is working, they have solutions, they're just refining it more and more, where even for 2G they can get rid of the SAW, don't filter those far away strong blockers that I showed earlier, right? The far away blockers could be we could go as high up as 0 dBm, and if you don't have a SAW filter, that will come and hit the LNA directly. So your signal is so weak, say minus 110 dBm, and your blocker is really strong, it will go through some filtering and some matching and all that you do here, the matching circuitry as we'll talk about. But still, if you can get rid of the SAW, which is a few cents there, that's like a cost benefit, especially for 2G, because 2G is in the lower end of the spectrum. Also in terms of money, these markets are not the high cost markets, they're the low cost markets. So there is a lot of room for innovation to make SAW-less transceivers. Duplexers you can't avoid. If your path is doing a UMTS type standard, whether it's TX and RX on at the same time, you just need the duplexer. You cannot get rid of it, at least not now that I know of. But when you're doing the 2G GSM type, where the receiver is on, the transmit is on, the SAW is the filter that is trying to filter out the faraway blockers. If you could do a SAW-less, where you can handle those blockers doing intelligent things in the design, that is one of the things that a lot of the folks in the industry are working on the SAW-less transceiver designs. So I just wanted to make a point on that before going to the next section. Okay, let's continue on with to look more into the blocks, right? So we looked at this picture earlier, and I've tried to highlight this block, which is what many of the companies design it as their RF transceiver. It has the RF and analog block, and the digital part goes in a separate digital chip or a die. Sometimes some companies also combine the whole thing and make an SoC. But here I'm trying to highlight this to kind of go into more details of what does these blocks look like typically when we're trying to make this world phone type transceivers with all these complexities. What does it actually, some of the common architectures, what it looks like, and give you some details. Since this is a very competitive field and a lot of proprietary stuff is there, I will not get into too much details of any of these blocks, but we will focus on these and let's look into some of the details. So first let's start with the LNA. Okay, and I'm sorry, my tool is not working which can draw, so I tried to draw by hand and put a scan picture here, and I will try to walk through each and every element and try to make sure I cover all the important points here. So first of all, the LNAs that we are using here, these are the narrowband. They use the narrowband input matching type topology. Why? Because as we have seen, the lowest frequency bands in some of them could be as low as 450 megahertz. So you could be receiving something around 450 megahertz, which is the CDMA 2000 band, an old band, not so much used anymore, but still, it needs to be supported in many of the chips, low-end chips. And the highest ones, the China market has 2.7 gigahertz. It's pretty high, and there are actually even more bands coming up which need to support even more than 3 gigahertz. So there's a wide spectrum of different bands that has to be supported, and we cannot really do that with a wideband LNA topology. They are all done with narrowbands, okay, type of matching. So they all use narrowband input matching, which is what we'll talk about here, and they also use LC tuned output load. So let me go to this picture and say what I mean. Okay, so if I start from the left, okay, so this is on my PCB board. So I come in, and typically they have an external matching circuitry. Okay, this is what I'm trying to show as a 3-element matching. Okay, sometimes you might need more than 3 elements, you might even have 5 elements, but let's just keep it to 3 elements for now. So they will have these slots to put either an inductor or a capacitor or a resistor, okay, in these slots. Typically what happens is, if you remember a narrowband LNA, right, which is what is shown here, okay, so this is the pin, okay, the package pin, and then it goes inside. There is some sort of a biasing circuitry here which takes a bias current, filters it out to make sure all the noise and everything is filtered out by this RC filter, and then it biases this guy, which is a simple NMOS amplifier with a cascode for isolation between input and this is the output. Okay, so the narrowband matching that I'm sure you're probably familiar with it already is you use an on-chip inductor. This LS is an on-chip inductor, and you also use an off-chip inductor. So let's say this element was an inductor L. This is off-chip. This is my package pin, and anything on the left side is off-chip. So these two inductors, along with it, it will see a capacitance here. In this case, the CGS, gate to source capacitance. With that, it will resonate, and you can design this LS and that L inductor, choose the external in such a way that the total L along with the total CGS resonates right at the frequency where you want it to operate. For example, let's say the most common band is band 1, which is around 2.1 gigahertz. So you have to make sure that this L, the total combined L, this L, external L, plus this L along with the CGS, if you do the LC product and do a square root of it, which is the resonant frequency of an LC circuit, it should be 2.1 gigahertz. Okay, that's how we do the matching, and of course at that frequency you also get the impedance looking in, right? Your source here is 50 ohms, so you're trying to see 50 ohm looking into it, and that becomes the product of the GM of this device multiplied by LS divided by CGS. Okay, so GM times LS multiplied by divided by CGS gives you, should be 50 ohms roughly. Okay, that's the initial starting point. and that helps, you look at 50 ohm and you get the impedance matching, and typically in all the theory cases, you can do it with a single element match. But typically why we have this kind of a network is there are lots of other capacitance that comes. There is bond wire inductance, okay, there is inductance on the PCB boards. Some of the traces could be very long, and that's one of the challenges I'll talk about in more detail. So you could have a lot more parasitic inductance, you have capacitance, you have ESD here. So ESD is always associated with parasitic capacitance that comes in. Okay, the package pin itself, based on what kind of a package it is, if it's those fancy packages we have nowadays, which are like the wafer scale packaging, then you have very low parasitic capacitances. But if you go to old type of packages like QFN or others where you actually have leads coming out, right, that will have more parasitic caps. So with all those things, a single element matching, what we study in theory, does not really provide good results. It will work at lower frequencies, and by low frequencies I mean maybe around 900 megahertz. Those type of bands it works. But when we go to higher frequencies, all these parasitic inductances and parasitic capacitances, you cannot just match it with a single element. There you might need some kind of a matching topologies, like you might need a shunt element. The shunt element might be an inductor or a capacitor, okay. And if you find out that, okay, I don't need a shunt element, then DNI means do not instantiate. This is kind of a term we use in the industry. Is you have an empty slot, you can put in an element and solder it, okay. If you don't solder it, that's fine. I mean, if you don't put it in, then that becomes as a DNI, which is telling do not put anything there. I don't need that slot, leave that slot unused. So this is for providing a series element for matching, could be L or C. These are for shunt elements, could be an inductor or a capacitor, based on this all depends on how you are positioned on the Smith chart. Okay, so and again I'm not going into those details, but if you are at different locations of Smith charts, you might need an inductor with a capacitor, in series or parallel. There are different kinds of these topologies, that are there. So we just give the option off chip on the PCB board to be able to put the different kinds of matchings elements, or different kinds of configurations, different kinds of topologies that you might need to put elements there, or just leave them empty, which is called do not instantiate. Okay, so that is the external matching. That is the network shown. I already talked about it while I was trying to talk about it, I guess. This is the simplest configuration of the LNA that is used here. Okay, and this has got an output load. So what the LNA is doing is it's taking a voltage and converting into a current. Okay, and that actually goes into the mixer, which we'll look at. Mostly it's a passive mixer. So this actually acts as a GM stage. This is tuned load. This is LC, and the LC product is again tuned to that respective frequency. Like if you're trying to match the input at 2.1 gigahertz, that is where you're trying to receive, you will also try to tune this at 2.1 gigahertz. Okay, because then if you work it out, you will see that the losses in this kind of a structure, the transformers, are least, and most of your current that's coming out here will go out to the mixer. If you look at it in form of current, if you look at it in terms of voltage, when this LC tuned circuit resonates, it provides the highest impedance possible, which is the RP. Of course, even if I say highest impedance, it's not really so high. It might be in hundreds of ohms. That is based on the RP impedance. If you take the RP, that becomes the combined Q of this circuit times L, the inductance value, times omega. Okay, whatever the frequency you're resonating at that point, that gives you the RP. So it doesn't, I mean, it probably could be 500 ohms, 1 kilo ohm, something like that is probably some realistic values. But anyway, so that is the output. Okay, so we have the matching, we have all this. What is not shown here is this LNA will also need, so remember the input, the signal that comes in could be as weak as say minus 110 dBm for WCDMA. Okay, but it could be as high as 0 dBm. So just a configuration like this is not going to be able to handle all the input power levels. So we have to have some AGC or gain stepping here, gain steps. Okay, that is not shown in this picture, but just to give you an idea and hint is we have to find different ways to change the gain of this LNA. When the signal is low, it should provide the maximum GM or maximum gain. When the signal gets stronger, you have to lower the GM, lower the gain, so that this guy can actually handle it. Okay, how I cannot go into exact details of how we do it in the industry, but I think you can look in the papers and all, and you know, some point if you and I get to talk to separately, then I can give you show you some pictures. Okay, so how we do it. So that has to be also implemented here, which is the gain stepping, to make sure that we can handle a large enough dynamic range. Okay, some of the other key points that I want to mention here is, so typically one of the things that must be surprising to you, but it is really good. The designs have come a long way and the performance has come a long way, and I thought that I would highlight it so that you guys know about it. You know, the literature says a lot of different kind of numbers, but let's say the noise figure. So you have a receiver, you're trying to build the best receiver. What kind of noise figures these commercial products actually achieve? So if I take the noise figure of the whole RX chain, not just the LNA, okay, I'm talking about the LNA, then there is mixer, and then there is here. So if you include the noise from the LNA, the mixers, the baseband filter, ADC will also have some noise. So all this noise, if you take and you reflect it back to the input of the LNA and you say, you know, tell me the noise figure. These typical guys achieve a noise figure, a combined noise figure of about 1.5 dB. It's extremely low, and this is for low band. Low band is around, you know, where it's 700 megahertz, 800 megahertz, 900 megahertz. Those are the low band frequencies. Okay. Now when you go to higher bands, high bands, like say band 1, the most popular band is 2.1 gigahertz, or you're trying to go 2.7 gigahertz, then they do degrade. It's hard to get that much gain at higher frequencies, so obviously the noise will go up, and they could be somewhere around 2.5 dB. These are the typical numbers that you will get. These numbers will vary over temperature. So this is more at room temperature. If it gets hot, at hot condition, this might degrade by another half a dB. Okay, and also over volume. You know, when you make something, it's not always typical process. You know, the process corners also shift. The process could get slow, the process could get fast. So typically when the process gets slow and it also becomes hot condition where the noise is always higher, in hot condition, you could deviate almost a dB from these numbers. So if you say typically you get 1.5 dB, you can think that over millions of parts and over temperature, this might become 2.5 dB. But this should give you some idea of the cascaded noise figure of the whole RX chain, what kind of numbers these commercial products actually hit, and that's how they are designed. If you consider the LNA by itself, that itself is less than 1 dB, and it has to be. So the LNA by itself is less than 1 dB, and you know, the combined chain, you know, all the other noise contributors come in and give you this kind of numbers. So that is in terms of the noise performance. Linearity. Linearity is another key thing that I wanted to kind of share with you, because LNA is the first one, right? LNA is taking the hit, and when strong jammers come in, some of the strong jammers get filtered by this this matching network here. Oh, there's another thing I forgot, and I think I should mention it, so I will go back a little bit. So let's not talk about linearity right now. There is one other point, key point, that I forgot to mention here about this. Okay, getting these extremely good noise figure numbers. One of the benefits we get from narrowband input matching, right? So this is only matching at a narrow band of frequencies. When you do that, the matching circuit actually, if you look at my other lectures, which are on YouTube, or you look at the literature, you will see the matching circuit actually provides gain. So narrowband matching is actually a free advantage that comes by doing this narrowband matching. Is not only you've done the matching, you actually provide gain in the circuitry. So imagine a passive circuitry providing you voltage gain. Okay, if you have voltage gain in front of this, all these circuits here which are creating noise, right, that also helps a lot to suppress the noise, and that is one of the key reasons why narrowband matching is very good and widely used, is because the gain in the matching circuit helps lower noise. That's great. And the other thing, as we will see, is that matching circuitry is also acting as a filter. So some of the far out jammers that will come, it will filter it out. Okay, so it only provides good matching at such. So let's say you're matching at 2.1 gigahertz, and you had something at say 2.5 gigahertz, some interferer. This matching circuitry actually will provide significant attenuation of that. maybe 10-20 dB, not a whole lot, but still good enough to attenuate it. So those are the key things that come from narrowband matching. If this was wideband, you will not have the gain, your noise figure is going to be bad. Okay, your design, and that's typically the problem with wideband LNAs is they provide matching for a wide range of frequencies, but they inherently have bad noise figure. You have to burn more power to lower the noise, and also their jammer performance, jammer ejection, is a little worse off compared to the narrowband type structures. So that's another point I wanted to mention here. So let's go back to linearity now. So as I mentioned, linearity wise, this provides some filtering, but still the jammers coming in, they hit the LNA. So the LNA has to be, LNA is the first guy who gets hit by it, and its linearity specs, especially the IP3 in this case, is critical. CDMA 2000, when the standard was written initially, right, it had some really strong jammers, and that drove some really strong linearity requirements, where the LNA IP3 needed to be almost around +8 dBm. That is crazy high, okay, to implement in today's technology. In those olden days, when it used to be like 0.25 micron CMOS or 0.18 micron CMOS, or even the bipolar technologies, these numbers were hard to hit. So you couldn't just hit it with an architecture like that. There are different schemes which are there, where you actually help boost it. So this could be your main path. You could have schemes called MDS, modified derivative superposition. That was one of the things that we used widely to improve the linearity. You can look at it, but there are different kinds of schemes which were used to actually provide a very good linearity, like +8 dBm type of numbers for this LNA. And when the LNA was able to meet that kind of linearity, which is for CDMA, it could meet it for any standard. But now this spec has been relaxed, and if you look at CDMA or WCDMA standard or LTE and derive all the different jammer scenarios, and then you calculate the IP3 needed, the linearity requirements needed, and you take the toughest of all. This is only one LNA. This is going to support, in a particular frequency band, it will support GSM, it will also support CDMA, it will also support WCDMA, LTE, everything, right? So we have to design it to meet the highest, the toughest IP3 number, and that's what we do. And they typically come to around 0 dBm or less than that, typically. So that is realistic, could be designed, and the circuits have become very simplified like this. We don't need to achieve very big IP3 numbers, and so that's with the linearity, and that how much could be the numbers, and again these numbers come from detailed, you take all the jammer cases, you do a detailed analysis, and you'll come with it. But I just wanted to give you an idea of what kind of IP3s that these are designed to meet. So now we know about the noise figure and the IP3 numbers for the LNA. So hopefully I've covered most of the key things for this block that is achieved in today's all these multiband multimode transceivers. Next is the mixer, and the mixer is actually again, if you have referred to my other lectures in this thing, you must have seen it. So we have this LNA that we talked about. The LNA is actually a GM stage which provides a current. It has an LC tuned load at the output, and with that you go into these mixers, which are followed by what we call baseband filters, or these are like low pass filters, okay, to provide some filtering of the jammers. But if you look at this mixer, the reason we have two is we have an I and Q channel. That's why I showed two of them. It just looks like an array of 4 simple switches, and what we are doing is this is the inputs. This input point is actually this point where the LNA current is coming, okay, the positive and negative. And this LO is actually a square wave signal. Okay, we don't drive these with sine waves, we drive them with square waves. So you have a VCO generating the frequency, and then we have a set of buffers which is squaring it up, and finally the square wave comes here. This either turns on the switch really heavily hard or turns it off. Okay, when it's turned on heavily hard, it is supposed to be almost like extremely low resistance for these switches. Okay, so again, I will not go into how this thing works, because if you want, you can refer to my other lecture which is on LNA and mixers, which is also on the YouTubes, and you will understand more of the operation there. But what is key here? The key here is the IP3 of the switches have to be extremely high. Remember, there's gain here. Okay, so let's just think that somehow from input to output the gain is 20 dB. Okay, then if at the input you're trying to get 0 dBm type IP3 number, so 0 dBm here with 20 dB gain tells you roughly that this IP3 has to be plus 20 dBm. That's why the switches need to be designed to have extremely good IP3. Now what does that mean? See, this is a switch. The switch, the lower the resistance is, right, the better the linearity is going to be. That's just the fundamental thing about these switches. So how do you make the lower resistance? Well, you increase the overdrive VGS. So when you turn it on with a strong overdrive. Well, there is a limit to it, how much it can sustain before it breaks down in these today's technologies. So you can't just put a huge voltage number here, right? So what do? The only thing left is you increase the size of the switches. But when you increase the size of the switches, then your power goes up, right? Because this LO, it's going to have a dynamic power happening because it's switching it right on and off. So whenever something is switching on and off, there is a dynamic power associated with it, which becomes also it's the current that's being drawn from the battery, and that tends to become higher. So we can't even make the switch sizes too big. So there is a compromise where you have to find, do a few tweaking and find out that okay, this is good enough. And we are also able to get the IP3, but what is more important here is actually this bullet here. Okay, IIP2, in these commercial products that are there today, the IIP2 is the most important spec, which is very, very difficult to meet. And what is IIP2? So what happens is, in this case, right, if all the 4 switches were perfectly balanced and matched, so you have some W and L value, and let's say all 4 are matched, then you will get a perfectly nice, you will have the fundamental component, you will not have any second order component, you will have the third order component, you will not have any fourth order component, right, because it's a differential, so it will cancel out all the even order harmonics. But given that we have finite switch sizes, okay, so let's take an example. Let's say you're designing in 28 nanometer, where the lengths could be 28 nanometer because you're trying to keep the lengths the smallest, and the width could be, say, just as an example, say 10 micron total width. Okay, many fingers and all, multiplicity, whatever you have, total. So you have the total width as 10 micron, and the length is say 0.28. Okay, so the matching now, so with these kind of numbers, it gets turned on heavily, and you're able to meet the IP3 number. Okay. With those kind of numbers, let's assume that the power is also low. There is not enough parasitic capacitance that you have to switch on and off, so power is also low, so that's also good. But what happens to the matching? So if you have a width of say 10 micron and the length is 0.28, and you multiply the two, right, the area, so the gate area is roughly 2.8, right, micron square. And if you look at how the matching goes, matching varies inversely with square root of area. So square root of that, so the total area of 2.8 micron square is actually very small. That's what I'm trying to say. What that means is every technology has those numbers that how much mismatch will happen, and from there if you derive it, you will see that, oh, this could have significant mismatches. I don't know how much, maybe 2%, 3%, 5%, 1%, I don't know, it's based on the technology. But the key thing is, as the length has scaled down, the product of length and width, right, which is the area, has also scaled down, and they are causing significant mismatches. Whenever there is a mismatch between these switches, your even order terms will not cancel out. They will be there, especially the second order. And when the second order term is there are many cases where the second order term will actually appear as noise. Okay, how does it appear as noise? Again, I'll have to ask you to refer to my other videos on the RF systems, which is also there on YouTube. You can look at it. And there we require a very tough IIP2. Okay, so IIP2 of these mixer switches is probably the biggest thing that we go round and round and round and round about, try to solve it, but still at the end, in some of these scenarios like LTE, where the jammers, okay, the TX itself, now remember in LTE, you're trying to receive, but your transmit is also transmitting, and it could be transmitting at pretty good power. So if you go through all the system level calculations, you go through the SNR that is needed, LTE will need more SNR, and you put everything together, you would get IIP2 numbers in the range of 50 to 60 dBm. And this is actually very high. Just by design, just by making the switch sizes bigger, we are not able to achieve it. A realistic number is more like 30 to 40 dBm. You can achieve it in, let's say, whether it's 65 nanometer, 45 nanometer, 28 nanometer. But once it numbers goes this high, there is only one way to achieve such big numbers, which is through factory calibration. So what we do in the factory is every phone that is made, right? Every phone goes through a calibration. We do many things, we calibrate many things, and one of them is this. So we'll actually put two close by tones to that particular phone. So we load up the phone on the setup, the phone, measurement equipments and all. We'll put in two inputs, we'll measure what the output is. Okay, in the output we will try to measure what is the second order nonlinearity that is there. And then what we will come back is we will do a few things here. I can't tell exactly what we change, but we will do a calibration here, because why we're doing the calibration is we already know there is an offset, right? There is a mismatch that exists here. We try to counter it by artificially applying an opposite mismatch. How do we apply? Of course, we can't change the device sizes, but we can change other things like voltages and currents, or some biasing voltages and currents. And when we do that, we are trying to counteract the mismatch in these devices by applying an opposite mismatch in biasing voltages and currents for these switches. Okay, when we do that, then we are able to lower the second order distortion that is produced here. And when we lower it, the IIP2 goes down. So let's say if a phone comes up and it has an IIP2 of only 40 dBm, we will run through this long testing, okay, on the factory, which is what we are calling calibration. We are applying some input, we are monitoring the output, going back, changing some digital programmable codes here, changing something in the circuitry and doing it in this. So this is the process of factory calibration, which every phone has to go through. Okay, unless you have an automatic way of calibrating it, that's different. They're trying to come up with it, but still I'm not aware of it that those things are completely working. So when you do anything in factory calibration, that's time, that's a lot of money. Okay, so when and imagine if you're making 100 million phones and you have to do every phone this way, that takes time, and that is money. It takes only a few seconds, but still that's a significant amount of money. Okay, so that is the key thing that we need to worry about in the mixer, and what are the things we can do. So there is a lot of work that goes on, and how you can improve it. There is a lot of techniques, and there's also a lot of stuff in the literature to do that you can look up. So this is the mixer. Then comes the baseband filter. Baseband filter is the one that follows after the mixer. Okay, so the main purpose of this is we are going to go to the ADC, but before going to the ADC, you try to filter out the interference, the various jammers that you have. Okay, so right after the filter, what we do is typically, even before going to the filters, we will put some caps. These are for trapping any RF. The LO that is here, right, the LO could leak here, the RF could leak here through the mixer switches. We want to trap it, and we put it in more in a common mode. So these are called common mode traps, common mode caps, to provide a low impedance for the RF signal. Okay, but for the baseband signal, which is the down converted signal, which is RF minus LO, that goes through here. If we didn't have these caps, then some of the RF signal will also leak here, and we don't want it. Even though the filter will filter it out, but it's something that we just don't want it to go to the baseband side. That's why we put these caps. So this is a trap for RF, and this is the way the baseband, the down converted signal, goes. The first stage is typically an op-amp RC filter, which is highly programmable. It has to provide different bandwidths. Okay, for example, in GSM, it could be a simple RC pole. Okay, here we have an RC pole around 200 kilohertz. Okay, but when you go to LTE cases, let's say LTE 20 megahertz is the biggest, the frequency, the mode there. This could become a second order filter. We might need both the stages, and the first stage might need a pole of around 5 to 10 megahertz based on where the jammers are. So imagine programming this RC product from as low as say 200 kilohertz all the way to say somewhere from 5 to 10 megahertz. That's a lot of programmability. When you add so much of programmability, these become discrete banks of capacitors and discrete banks of resistors. All this add a lot of parasitics, and there the challenge is, how do you design an op-amp which has a good enough speed and is also stable with so much of parasitics hanging at your input and the output? That is where it becomes a real challenge to design these op-amps to provide all these different programmable modes. So that's so again, as I mentioned, is that this is a generic topology. You could provide two poles here, or you could even have more stages to provide a higher order filter. You can also provide, by putting something like this, you also provide some fine tuning of gain, which is like PGA or VGA. You can do some fine tuning of gain of the whole RF chain here by doing this. And these guys are all highly programmable, and it puts a lot of pressure on the op-amps to how are we going to design it, keep it stable and actually burning less power, right? Power is important. You can do all this, but it increases the power consumption in this guy. Okay. The other thing I wanted to mention is this R's and C's that we're doing, right? These are also tunable over process corners. You know, these are, when you make an R, which is mostly a poly resistor, and the cap could be a MOS capacitor or you know, a metal type capacitors like MOM caps or MIM caps. These will always vary over process. You know, caps could vary plus minus 10%, 20%. Resistors could vary plus minus 20%. So when that happens, imagine if the resistor varied 20% and the cap varied 20%, you have varied 40%, right? So a variation of 40% will actually cause more than 40% variation in the pole location. That's not going to be good, because you're trying to put a pole, and if the pole varied more than 40%, then either your bandwidth is too low, your bandwidth is too high, and that you will not be able to reject the interferers, because that's the main purpose. We are trying to define a filter shape which will reject the interferers before it goes to the ADC. We don't want those interferers to saturate the ADC. So if these poles or the whole filter characteristics moved around so much, it's going to be a problem, right? That's why what we try to do is we want to preserve the filter characteristics. We want to do tuning, automatic tuning of these R's and C's. That is, if the R value varied by, say, some X percentage, right, there is an on-chip detection and an algorithm to actually come and tune this R. Okay, so this is how we do it. We tune the R's as well as we tune the C's, so that we maintain the pole locations and we maintain the filter characteristics. That is, if you needed a far out rejection of some value, right, we want to maintain that value over all these process corners. So that is another thing that I just wanted to mention. And by implementing all this baseband filter, this baseband filter is actually one of the most complicated blocks in the receiver chain, because of all these programmable modes that you have to support for multiple. So in a particular band, all these different modes that you have to support, and then on top of that it has to be tunable, right? And all this makes it is a very big, also power hungry, and one of the most complex blocks in the receive chain. Next we go to the VCOs, and typically the VCOs, type of VCOs we use are the LC based VCOs. Why? Because VCO, what is the VCO trying to do? This is on chip, it's trying to generate a very accurate frequency with less noise. So the noise requirements are very stringent for the cellular type applications. And the ring oscillator based VCOs are the other type of VCOs. They are not able to really meet it. That's why, because these extremely stringent ones, we use LC VCOs. Okay. And as we have seen previously, going through all our diversity, receive diversity, LTE carrier aggregation, SHDR and all that, there could be as many as 4 receive VCOs that could be there, and maybe just 1 TX VCO. Based on, again, how complex the TX is, this will be more also. So if you have so many VCOs and they are all LC based VCOs, you can imagine that all these coils on the chip, the more coils you have on the chip, the more inductors you have on chip, that is a primary source for coupling and spurs. So that is the first challenge we face in all these VCOs, is how are we going to put more and more coils on the chip but still not couple. Okay, so coupling, both magnetic as well as electrical coupling, becomes a really big challenge. So isolation is where the key comes in. So when you make these big systems, of course, let's say you put everything together and all, but then there's a lot of effort, humongous amount of effort goes in to study isolation, to carefully, with experience, do things which are right and not to do things which are wrong. That goes in floor planning and architecting and routing different signals around this massive chip. So that's where a lot of the experience of the senior guys doing it over many products help make these chips work. So that is something, there is no tool or way to do it. You just have to look at it manually and do the right things. So anyway, I think I was just getting a little bit off track on going to this isolation. We'll go for it more and more, but let's just look at typically what the structure looks like. So here is a VCO, a simple CMOS type VCO core with an inductor and maybe some current source. Okay, and it is electrical isolation is very, very important. That is, this VCO could pick up something from another VCO, okay, through the supply and ground. So supply, you can put LDOs for isolation. So it's electrically isolating from other VCO to this VCO or vice versa. There is a reverse isolation also. So by putting LDOs, we try to isolate the supply. The grounds, well, the only way you can separate the grounds is just use different, package balls, package pins. Give the VCOs different pins. Don't combine the pins, otherwise it's a direct way of coupling through the grounds. So electrical isolation means isolation through the VDD as well as the ground. So here is the core, we talked about it, and here at this point you will see sinusoidal signals, because as the LC oscillator, all the fundamentals it says, these are going to be oscillating like sine waves, but then we put it through simple buffers like this, which will make it square wave. Eventually that is what is going to be going to the mixers. Mixers don't use sine wave, they use square waves. So I've just put some simple buffers to show. Of course it's much more complicated, because after this you're going to have many dividers and all that will come. We'll talk about it. What else is there here? Well, again, okay, so to get into the details of the VCO, I have another set of lectures on the VCOs again, so please refer to it for more and more details. They are the same structure as this, which has a discrete cap bank, then it has a varactor and a V-tune. A tune voltage comes in the whole PLL loop, from the charge pump loop filter and all that. So please refer to that, but I'm just trying to show a very basic generic topology of what these VCOs look like, and to talk about the challenges. And let me go back to the challenges again. As we were saying, is the main challenge is isolation. Okay, there is magnetic isolation. So if you have two coils that are close by, two VCOs close by, they're going to couple to each other. So the only way to actually improve magnetic coupling is through orientation and physical separation. Physical separation is the main thing. So how much can you physically separate them? Well, the further you go, better it is, but the chips are so small, how far can you go? Right, if you have got like 5-6 different VCOs. So it's the physical separation which helps with the magnetic coupling, and then we have a lot of these electromagnetic tools which actually do analysis and show us that how much coupling is happening and how much it would degrade and things like that. Electrical isolation, as I mentioned, is they are all having their own localized LDOs to make sure they are all electrically isolated through the supply. Ground, you just put the separate package pins for it. The other thing is, because there is going to be coupling, which is also what we call as pulling, one VCO will be pulling the other VCO. One thing we never use is 1x VCO. 1x VCO means the frequency that goes to the mixer, okay, let's call it a mixer LO frequency, that is never going to be equal to the VCO frequency. If the VCO frequency, okay, was equal to the LO frequency, then that's called a 1x VCO. But what we do is we never use 1x VCO. We will always use something like, after this VCO, right, we'll use either a divide by 2, divide by 4, or divide by 6. So let's take the case, if we had a divide by 2 at these outputs, right, these outputs go to a divide by 2 circuitry and then gets fed to the mixer. Then the mixer LO is actually half, okay, half frequency of the VCO frequency. Okay, if it was divided by 4, then mixer is actually running at 4 times lower frequency than the VCO frequency. So this way, like, by providing these dividing ratios, we can make these VCOs operate at different frequencies, far away frequencies, because they could have different division ratios after that. And that also helps with coupling. They are not going to be in the same frequency, like close to each other. When two VCO frequencies are close to each other, they're going to pull them really hard. Okay, one will try to knock the other one really hard. But if they're far away, then one cannot really knock the other one so hard, because these VCOs, they have very high gain at very narrow band of frequency, right? So this is an LC circuit. This is like a high Q, extremely high Q LC circuit, which will have high gain only at that resonant frequency. But if you went far away, it will have, the gain would actually go down. So it becomes less sensitive to far away frequency. It's only more sensitive to frequencies which are very, very close to the oscillation frequency. So by separating these different VCO frequencies, by using these dividers, we make them more robust, less sensitive to each other, pulling each other. So that's one part. And of course, on top of that, we have the LDOs for, isolation. Magnetic isolation, as we mentioned, magnetic coupling is done through shields across inductors. So we'll put shields around it to trap some of the energy going out. And also the main thing is the physical separation. The more and more separation you can get, the better it is. But again, you're limited. The chip is not really big. These transceiver chips are really small. They used to be like 50 square millimeters or something, then they came down to 30, then 20, and now they're almost like in 10 square millimeter. Okay, so take a chip which is about 10 millimeters square, roughly 3 millimeter by 3 millimeter. Okay, how much distance do you have to separate these guys? And these are not the only things on the chip, as I will show later on. It really does become a challenge. So all these chips, making them work there is a lot of effort to actually get the blocks in, get all the innovations in to get very good performance. But even on top of that, these chips, the main thing that is turning out is going to be coupling, spurs, isolation, how you floor plan it, how you do all these things. There is no specific or defined way of doing it than what you've learned through years of experience. That is becoming the key thing in making these chips work or not work. So I think we talked about enough of this VCO business here, and you understand what it looks like. And again, refer to the other lectures for more details on the VCOs. VCO distribution. So this is what I was talking about. So let me try to see what happens, what I'm trying to show here. Okay. So let's take the example that we're trying to make this world phone, which has got so many LNAs. The previous example we saw were like 12 LNAs. Okay, 12 receive paths. So this green block. Imagine that this is the green block which is going to house all those 12 different LNA paths with mixers and baseband filter. Okay, that's what I'm calling as the RX signal path. Then you have the TX signal path could be here with, we'll see the TX part, how many are there and all that. So that is a path. Then I'm calling this red block as the RX synthesizer. This is where we might have, let's say, up to 4 VCOs to generate 4 different frequencies. You could have primary diversity, and then you could have all these carrier aggregation scenarios which might need, so you could have that there, right? And then you have the TX synthesizer here, which will also have 1 or 2 VCOs to generate the frequencies it needs. So if this is a red block where we have the VCOs, as we talked about previously, right, they are all electrically isolated as much as we can do with the physical separation, that is the magnetic isolation. We have achieved it. Still we have to route all these lines, right? That has to go through it. It need not be only 2 lines. It's actually going to be more than 2 lines, but I'm just showing this as a representation of the VCO that has to be run. It is never a good idea to run high frequency clocks, and by high frequency clocks I mean somewhere around 5 gigahertz type clocking signals all over the chip. Okay, that just increases the potential for coupling into the substrate and from the substrate going somewhere else, or coupling from metal to another metal or some circuitry next by. So how do we run these long signals? How do we distribute these VCO lines, right, to run long distances? By long distances it could run a few millimeters. As I said, that this chip could be roughly say 3 millimeter by 3 millimeter. If it was close to say 9 square millimeter area, that means if each side is 3 millimeter, this could be running 2-3 millimeters long from one end to the other end. So first of all, driving the line itself is a challenge. Okay, and then when you run a line that long, you will do all kinds of shielding and all kinds of good stuff that you want to do, but still coupling becomes a challenge. So when it comes to routing the LO lines or the VCO lines, what do we want to do? We want to keep them small. But when we try to keep them small, then what goes against that is that we want the VCOs to be on one side and the signal paths to be on one side. We don't want to mix them, because these guys are aggressors, right? They are oscillating at very strong signals, and the receive path you could easily couple to the LNAs if it was close to you. So there's a lot of trade-offs that has to happen, and in a scenario like this, coupling to very sensitive blocks, as I said, is important. So how do you floor plan them? How do you keep these routes away from it? So sensitive blocks like LNA, we want to keep it away and do the best job that we can. Okay, the buffers. Now when these lines have to go this long, these buffers are driving high frequencies. They also burn significant amount of power, and they also have stringent phase noise requirements. So when you run a signal, let's say you have a square wave after the VCO, and you divide it by 2 or whatever it is, and you have square waves. Whenever you run a square wave along a long line, it will go through the RC losses and also some of the inductance losses which are there. So all these losses will actually make your square wave look more like a with slow rise and fall times. And whenever you have slow rise and fall times, you're injecting more and more noise. Your phase noise goes bad. So to keep phase noise, to keep the sharp edges of a square wave, a sharp edge going up and a sharp edge going down, you need really good buffers to drive long distance. That means a lot of power. Huge amount of power actually in all these chips is spent on this whole VCO slash sometimes it's called as LO distribution. Okay, so this is an area which has a lot of details that the people have to work through to make sure they don't couple, they maintain the phase noise, and they burn a lot of power. For most of these things, long routes, we prefer current mode routing, and you can look more into it, that how you can route. When you route in current mode, you can get these signals to go long distance rather than doing voltage mode. So we're not trying to actually route a voltage, we're trying to route a current. Okay. These routes need to be properly shielded. They are mostly twisted pairs, so we'll do as twisted pairs. So if this was not like this, but we do it as a twisted pair, that would couple to any block which is next to it. It'll couple equally, roughly. Still, even after doing all this coupling, it's not, you can't avoid it, you just can minimize it by doing these kind of things. So this hopefully gives you an idea of a big chip. How would you floor plan it? How would you put the LNAs, just taking the previous example away from these things, because LNAs are sensitive blocks. We don't want these things to coupling and causing lots of DC offset type problems, and a lot of the details that go in here in making these chips work, because of these issues. Now let's also talk briefly about the TX blocks. The TX chain, as I showed previously, I'm trying to show the reverses. So there's a DAC. Okay, then after that we do the filtering to get the noise out and any kind of aliasing issue that will come up, because the noise, far out noise, will fold back. So you have to filter it out, and that's what these filters are doing. Then we have the I and Q channel, the two mixers. These are up converting mixers. Then we have a DA, driver amplifier, sometimes also called pre-PA, pre-power amplifier, and then we go off chip. Power amplifiers are off chip. This at this point could provide up to plus 10 dBm type output. That's how it used to provide previously, but now the PAs have more gain. So even if you provide up to say plus 4 dBm type of power, that's good enough, whether it's a GSM type 2 GPA or a linear PA, it's good enough. So this power amplifier, again, as I said, it could be a 2 GPA or a 3 GPA, and this is something that the manufacturer, the OEM like Samsung, will actually replace. When they make a phone to support 2G, this will be 2G PA. They will populate there. If it's not, then they will populate a 3G, right? So they make these different versions of the same, where at least you don't have to change the transceiver. And that's the main thing, is you use the same transceiver, change the BOM means bill of material, around it, configure the transceiver using software, from the baseband processor, and reuse that same hardware for supporting multiple frequency bands and multiple modes, multiple standards. So it always goes back to the same goal, is how less of a hardware do they have to swap around, right? That makes it that much easier for them to make these phones. So driver amplifier, we talked about it, the output, it's delivering into a 50 ohm load, because looking into the PA, it's 50 ohms. The key thing here is the linearity has to be very good. Okay, so these PAs have a requirement for linearity, like ACPR, ACLR type, because they're like 36 dBc. Okay, now what is 36 dBc? You can look it up and look at ACLR or ACPR, what does it really mean? But the key thing here is, when we design these are designed to be about 10 dB, at least 10 dB better than this guy. Okay, so if this has a linearity spec of 36, this will be 46, minus 46 dBc. That's how we will design this to achieve that. So linearity is very, very important, and the other thing is, which is very important, is the noise. All these things are going to add noise, and the noise is going to go out, and it's the far away noise. That is, we have the TX band and we have the RX band. How much noise is actually going to be there in the RX band? That is critical. That is what we call as RXBN, or RX band noise. Okay, so there is a spec for that also, and that actually eventually drives, right? So if you take the noise here, which is going to be in the RX band, it's actually far away. It's not in the TX band at all. It is further out, right? So if you take that number here, you say I want a number here to be, so and so, right? Some spec, and you divide it by the gain of the PA divided by the gain of D, and you bring it to mixer. You will see that eventually that tough spec for the RX band noise maps to the TXLO phase noise. the TXLO that comes here, its phase noise at that far away frequency, that becomes the biggest contributor of the noise at this point, which is what we call as the RX band noise. And that actually sets the spec to be very, very hard, you know, especially for 2G cases. And that's why the TX VCOs will always have a much harder phase noise requirement than the RX VCOs. So the noise becomes pretty critical, and it gets mapped mostly to the synthesizer. So that's all I had, and hopefully it gave you a good overview of all the things, you know, that these world phones, how do we build these world phones at the phone platform level, what are the various things we do, and also some of the block levels. We didn't go into too much into the block levels, but I would encourage you to look into the, you know, listen to the other videos which are there, which go into much more detail of these block levels. So I appreciate your patience and time for seeing these long lectures, and you know, all the best to you all. Bye bye.